Hi, my name is Daniel Olman, and today I'm going to be explaining the concept of lift through airflow visualization through my 3D printed wind tunnel, which I designed myself. In today's video, I'm going to be explaining Bernoulli's principle and Newton's third law of motion. And these two things state that Newton's third law of motion states that every force has an opposite reaction, while Bernoulli's principle states, kind of going off law of conservation, in which high pressured air and low velocity air tends to go beneath the airfoil, which I have right here, which I'm going to be demonstrating, and then you have the top of the airfoil, in which you have high velocity and low pressure. So these forces kind of lead to Newton's third law of motion, and they all kind of like work together to generate like lift. And then Newton's third law of motion, I'm going to be explaining through upwash and downwash and through physics, and how ultimately the airflow leads the wind in a downward direction. And like I said, every force has to have an opposite reaction. So in front of the wing, the airflow tends to go up, which starts generating lift, in which you'll see through my visualization of this wind tunnel. In today's video, I'm going to be experimenting with a couple different concepts of wings. So here I have my Concorde wing, and this is just a basic design of a Concorde wing. This project was designed to test the difference in generating lift and efficiency between the Concorde wing, because Concordes fly like 60,000 feet in the air, while commercial airlines, like for transatlantic, they fly like 40,000 feet in the air. So obviously there's a 20,000 or more altitude difference. So I wanted to test how each wing kind of generates lift on a small scale. And then here I have a typical airfoil to demonstrate airflow visualization. And then lastly, I wanted to test the concept of, so depending on the level of attack, which you can see I'm going to be able to rotate through that hole in the air tunnel. Depending on the level of attack, we're able to actually generate lift with a barn. Well, this is supposed to represent a barn door, but apparently you can generate lift with a barn door, so I'm interested in seeing how that plays out. The honeycomb shape makes the air less turbulent and straightens out the air so smooth air can follow throughout the tunnel. This is the contraction cone. This segment rapidly accelerates the air, reduces turbulent air, and straightens out the flow of air. This is the smoke rate, which enables flow visualization throughout the wind tunnel. This is the test section. This section enables us to see a visual of what is going on. This is the diffuser. The diffuser slows down fast-moving air and converts it into dynamic pressure into static pressure. This is the fan plate, which rapidly accelerates the air, almost creating a vacuum effect inside the test chamber. This is an airfoil. Airfoils are typically used to demonstrate flow visualization in wind tunnels. This is the shape of a Concorde wing. This is the shape of an Airbus A320 wing, otherwise known as a commercial wing. This is my representation of a barn door. Okay, so inside the wind tunnel, you can see that I have a regular airfoil, and here I'm using this airfoil to kind of describe Bernoulli's principle and Newton's third law of motion. So I'm going to be using a pen to illustrate how the projected air flows over the airfoil. And so at the beginning of the air tunnel, you can see that the wind or the smoke slowly starts coming up from the smoke rake. This is known as upwash. Following the airfoil, you can see that the smoke starts to have a downward direction. This is called downwash. So now I'm going to explain Bernoulli's principle, and this principle kind of goes off the law of conservation in which the pressure below the airfoil is going to be more than the pressure above the airfoil, and contrary to that, the velocity below the airfoil is going to be lower than the velocity above the airfoil. And so as you can see, the air starts to go faster towards the end when it's at the top of the, following the airfoil, than at the bottom. And then this is also because the air has to travel more of a distance, while the path that the air takes over the airfoil starts to circulate around the airfoil, which simultaneously slows down the wind coming from, or the smoke coming from the bottom of the airfoil. So now I'm going to explain how Newton's third law of motion kind of contributes to the concept of lift. And so, as you can see, the concept of upwash and downwash before the airfoil, following the airfoil. And so this principle just states that ultimately there's like opposite reaction to a force. And so, as you can see, that ultimately the air starts to slowly go downwards. So as I was saying, downwash. And so at the beginning, there has to be something that contributes the air going up. So that's kind of like using Newton's third law of motion to kind of illustrate the concept of lift. So now you may be wondering what is going on when the smoke from the smoke rake starts hitting the airfoil. And so this point here, when it hits directly at the airfoil, is called the stagnation point. And this is when the velocity of the air equals 0. So now I'm going to change the level of attack, and you'll begin to see how the upwash and downwash slowly start to change depending on the level of attack. So if I were to have the level of attack all the way down, this is what causes airplanes to stall. And so this is where it's not generating any lift and generating like ultimate drag. And so you can start to see just like complete upwash and almost no downwash. And then that's how airplanes drag. So they have stall, sorry, not drag. And then as I start to change the level of attack, you can start to visualize that airplanes kind of have like a minimum and a maximum.
Airfoils have a maximum and minimum angle adjustment level that can be changed. Surpassing the maximum does not contribute to anything and may cause the aircraft to stall.
So now I'm just going to change the level of attack more so you can start to see more of a visualization in the change in upwash and downwash, and how there is like a minimum and maximum the angle the airfoil can go. And so you can start to visualize that as I start turning the airfoil. So now, just to summarize things up and just leading off Bernoulli's principle, the pressure difference is what actually generates air. And this is why airfoils are so effective in generating air. It's because they're an asymmetrical object. And the reason why asymmetrical objects are so effective in generating air is because when they split the air, it's not equally distributed, the air. And so the pressure difference is what contributes to generating lift. And this is why changing the level of attack is what drastically makes a difference regardless of the airfoil. And so symmetrical objects aren't able to generate lift just because of the equal pressure that they create beneath and above the airfoil. And then, like I said earlier, the asymmetrical object is, and the pressure difference is what enables lift to be able to be generated. But just to measure like the curvature of the wing, which is called camber, to measure like where it's symmetrical, this is called the average camber line. And then the camber is just the curvature of the wing. And then finally, I just like to introduce you to two more terms called the leading edge of the airfoil and the trailing edge of the airfoil. And the leading edge is where you'll find the point of stagnation. Okay, so in the tunnel now I have a Concorde wing. And keep in mind, when I was designing this, I didn't design this Concorde wing being symmetrical. I designed it for the shape. And so that was my fault. However, as I change the level of attack, you can see a difference in the airflow. And the reason I'm turning it up is because I printed the wrong side. And so I had to glue it on the downward, like opposite of where it's supposed to be glued. So instead of it pointing upwards, it's pointing downwards. So I'm changing the level of attack upwards to kind of like contradict that. And then, as you can see earlier, it did. You could start to visualize the upwash and downwash, and it's clearly not as effective as the commercial airline wing, which is also symmetrical, like this Concorde wing. But the Concorde wing has the Concorde wing's real shape. So now, going off Bernoulli's principle, I'm going to be testing the velocity difference in meters per second that the wind flows in the Concorde wing. So above the airfoil, or rather below, because it's inverted, it's 0.9 or 0.8 meters per second, and below the airfoil, it is 1.1. So I would just round up to 1.1. So you can see Bernoulli's principle is demonstrated here, and you can see the difference in velocity. And if I were to have a pressure tester, I'd most likely be able to see the difference in pressure. And then here I'm just changing the level of attack just to demonstrate the upwash and the downwash. Okay, so now I'm going to demonstrate the theory of a barn door, and if you change the level of attack, it should, according to other people, say it should generate lift. And so we're going to test this theory. And so first of all, I'm going to measure the velocity at the top of the airfoil, and I'm getting a measurement of 0.6, 0.7. Then at the bottom of the airfoil, I'm getting a velocity of 0.9, consistently 0.9. And so this difference in velocity is because when it reaches the airfoil, the distance the air covers is way less than the distance that it covers at the top. And when it hits the stagnation point of the airfoil, it mixes up the air and it causes it to kind of be mixed up. And so that decreases the velocity as well. So first of all, this object is symmetrical. And second of all, it does not follow Bernoulli's principle. And so this is why this object isn't able to generate lift. And according to my wind tunnel, this theory would be false. So similarly to the Concorde wing, I printed this on the wrong side. And so instead of changing the level of attack downward, I'm going to have to change the level of attack upward to stimulate liftoff. And this wing isn't going to be as projected in a normal wing because it's symmetrical, in which I didn't account for, just like the Concorde wing. So wings typically have to be asymmetrical in order to generate lift. And so again, it was printing error. So I'm just going to test the velocity difference and see if it makes a difference. So above the wing, we have a velocity of 0.8, and below the wing, we have a velocity of 1.1. So now I'm just going to be changing the level of attack, kind of just to demonstrate again the upwash and downwash when it comes to a commercial wing. Obviously, this isn't the best illustration, but you can kind of see as I change that there's a slight change in the amount of upwash and downwash as I change the level of attack. So now that you've finished the video, I'm just going to give a more in-depth concept of how lift is generated and going more in depth with all the terms you've learned, such as the stagnation point, leading edge, trailing edge, then you have upwash, downwash. And so when the air reaches the airfoil, it gets split into two parts. And then ultimately these parts have to meet at the same time. So what happens is the air at the top has to go faster for it to meet with the air at the bottom because it covers more of a distance. So the velocity actually has to increase on top of the airfoil, which is what causes the pressure to decrease, while at the bottom of the airfoil, the pressure increases while the velocity decreases. So eventually when they meet up. Now, when they meet up, ultimately, they mix together and they have that downwash trend, as I said earlier, going off Newton's third law of motion, in which there has to be upwash for there to be downwash. And when they mix at this spot right here, this is called wake, and this is what causes like turbulent air after you start to have like patches of turbulent air because you have air going in different directions. And this contrast is what is able to generate lift, and this is why this shape of an airfoil can split the air and divide them and have pressurized differences and increase and decrease the velocity. And ultimately, this is what contributes to lift.